Hello everyone, hope you all are doing well. So in this video we'll discuss the third problem of Leetcode Weekly Contest 313. Again, a problem related to bit manipulation. Seems like the problem setters are really fond of bit manipulation. So I think every second contest we are at least getting one problem related to bit manipulation. We got it yesterday in the bi-weekly contest as well. That was also a good problem. This one is a better one, I would say. So yeah, yesterday also third problem was of bit manipulation. Today also the third problem is of bit manipulation. So yeah, let's go to the problem statement and then we'll see how we can approach this type of problem. So the problem name is minimum XOR. Given two positive integers num1 and num2, find the integer x such that x has the same number of set bits as num2 and the value x XOR num of 1 is minimal. Note that XOR is the bitwise XOR operation. Return the integer x. The test cases are generated such that x is uniquely determined. The number of set bits of an integer is the number of ones in the binary representation. Right? So yeah, let me just explain you and then probably we'll jump into the approach, not the solution, rather the approach. So you are given two numbers. Let's call it n1. I'm a bit lazy to write it num1, so n1 and n2. Let's consider it 5. So it says that we need to find a number x, right? We need to find the number x such that the number of set bits in this number and n2 is same. Like 5 is this, so number of set bits is 2. So you need to find number x which also has the number of set bits as 2 such that the XOR of n1 with x is the minimum possible value that we can get, right? Is the minimum possible value that we can get, right? Now there are multiple parts to this problem. The way I have solved it. So the first thing is you need to find the number of set bits in a particular number, right? That is altogether a different problem, but I'll just tell you briefly. So I'll also show that in the code. So how do you find the number of set bits, right? So there are multiple ways. One way will be the easiest way will be you traverse the number while n is greater than 0, and obviously if n mod 2 is not equal to 0, you do count plus plus. And at every step what you are doing, you are shifting it by one position to the right side or basically dividing it by 2, and this is a way you get the count number of set bits. Another way, a better approach, like this will be the time complexity again will be constant. It will be big O of 32 for 32-bit number. However, there is another approach. What we can do is we can do while n is greater than 0, and what you can do is you can do num. Again, let's write it n. So n equals to n and n minus 1 and do count plus plus. So what will happen? What this does is it removes the rightmost set bit of a number. Let's take an example just for clarity. Suppose a number is 101. I need to remove the rightmost set bit, right? So what is n minus 1? N minus 1 is 4. So 4 is this. If I take and, so it becomes 001. You see, the rightmost set bit is removed. Let's take another example. Any example we can take. Let's take 12. So 12 is 1100. So n minus 1 will be 11. What is 11? 8, 9, 10, 11. Yeah, this is 11. You take and, what will happen? This is 0, this is 0, this is 0, this is 1. You again see the rightmost set bit is removed. So at every step what will happen? The rightmost set bit will be removed. So the new number will become this. And again this bit will be removed. So the time complexity for this solution will be big O of number of set bits. Right? So a much better optimization. This was big O of 32. This is big O of number of set bits. So for example, if you have a number of 1 0 0 0 0 like 31 bits, so 32-bit number where you have 31 zeros and just 1 1, right? So what do you do? The time complexity for this one will be again big O of 32, and in this case it will be just big O of 1 because it is equal to the number of set bits, right? So yeah, this was how you find the number of set bits. Now just see what are the cases, right? When you know what are the number of set bits, then what are the possibilities? Suppose number 1, number 2, and for this the number of set bits is count 1, and for this set bits is count 2. Let's take what are the cases, right? Suppose count 1 equals to count 2. That means the number of set bits in both the numbers are equal. So what will happen? Suppose I have a number 5, right, and I need to find a number x which also has the number of set bits as 2. Here we have 2. I told we are discussing a case of ct1 equals to ct2. So that means I need to form a number having 2 set bits such that the XOR of that number and 5 is minimum. So what I can do, I have 2 ones, I can place these 2 ones here. If I take XOR, it becomes 0. The property of XOR is that if both the bits are same, you get 0. If both the bits are different, you get 1. So I have 2 ones. So what I can do, wherever I have 1, I will place 1 there, and at the remaining position I can place 0. So since the number of set bits in both are equal, we are discussing this case, right? If both are equal, so that means in this case I can directly return n1 as my answer, right? I can directly return that. You take n1 XOR n1, n1 XOR n1, and that gives you 0. So you return n1, right? What are the other cases? Let's consider ct1 is less than ct2. That means the number of set bits here is less than the number of set bits here, right? Now let's see what I can do. Suppose I have a number 1 0 1 0 0, something like this, and the number of set bits here is 2. And what about this? Count 2 is greater than count 1. So suppose here I have 2 bits and I total have 3 bits which I need which I need to use to form a number, right? I have 3 bits. So just think, to form the minimum XOR, what do I need to do, right? What do I need to do? The simplest stuff that I can do is I place 2 numbers out of these 3 numbers. I place 2 numbers here. Forget about the other numbers. So that means if I take XOR of these 2 bits, I'll get 0. I take XOR of these 2, I get 0. Why I am placing it here? Because to reduce a number, to get the minimum number, you need to remove the most significant bit. So to remove the most significant bit, what I'll do, I'll to remove that, I'll place a 1 there. Right, I place a 1 there, so that becomes 0. Now what about the remaining positions, right? What about the remaining positions? So just see here, I have 1 bit remaining, 1 remaining, right? 2 I have used, 1 is still remaining. So what I can do, I can start traversing from the right side, and as soon as I get a 0, I place a 1 here, right? Because the weightage of the rightmost bit is 1, the weight and just before it is 2, it is 4, 8, 16, right? Similar simple bit manipulation. So the rightmost unset bit can be set. I can place 1 there in my final number x, and that basically gives me the minimum number that I need, right? The minimum number I need. Now suppose I have a number 1 0 1 0 0, something like this, and I have 4 bits I need to use. So I'll place 2 of them here, and then remaining 2, 1 here, and 0 here. So this is my x. I need to return it. 2 bits I have used to make them 0, and then starting from right side, I place it here. However, if this would have been 1, so I would have placed 0 only here. I would have placed 1 here. Actually, this would have been 1 because I am replacing every 1 with 1, right? So simple stuff, nothing fancy. Now let's take an edge case. An edge case will be, suppose your number is 1 1, so you have 2 set bits. However, you need to form a number having 3 set bits. So what you will do, you will place 2 ones here. You still have 1 remaining. So you don't have any 0, right? So you are bound to place the remaining 1 here. So that means the minimum number that you will be getting will be 7, right? Just a tricky case where you need to place the number on the left hand side. In this case, you will be getting an answer greater than the existing numbers, right? So what all we have discussed? We have discussed ct1 is less than equal to ct2. We have discussed the equal to case. We have discussed the less than case. Now the only case remaining is ct1 is greater than ct2. I am doing the detailed explanation so that you understand how to approach this type of problem, right? Otherwise this can be reduced to a very small solution as well, right? But yeah, let's go to the approach. Now ct1 is greater than ct2. Suppose you have a number, just a second, let's assume you have a number 15, 1 1 1 1. The total number of set bits is 4. This is n1, and suppose n2 is 5. So you have 2 set bits, right? You have 2 set bits. Now what you will do? So just see here, I have just 2 set bits. So what can I do? I can basically as I told you, I need to make the leftmost, the most significant bits as 0. So I can place 2 ones here, right? And since I do not have any remaining ones, I can place 0 here. So it becomes 1, it becomes 1, it becomes 0, it becomes 0. This is the minimum XOR that you can get. And what is this number? This number is 8 plus 4, 12. So you return 12 in your answer, right? So for this case as well, similar to the above cases, what you are doing, just place ones on the most significant bit to make them 0. And then we are done. Now it all depends how we are doing it. So in the code, what I have done, again, since this was a contest, I was coding faster. So what I did, I calculated in this case what is the most significant bit. For that, I just wrote a function, and what that function does is it basically counts the number of set bits, and for the when it gets the last bit, what it does, it just returns the number. Like for example, if my number is 100, so it will return 4, because the power that this particular set bit has is 4. However, if it would have been 11, so it would have returned 8, right? It would have returned 8, because the leftmost set bit is 1, so 1 and 000, so it would have returned 8. So what I've done this, and then I'm making these things as 0, right? Basic stuff. Let's jump into the solution. So that's the approach that I've used. Let's start with the first function on line number 27. That's the main function. On line number 28, 29, you can see I have called a function get set bit count. I get the count of both the numbers, number of set bit. And on line number 2, I have built that function. Count equals to 0 while num is greater than 0, count plus plus, and num equals to num and num minus 1. Again, we are removing the rightmost set bit. The time complexity will be relatively lesser, but yeah, it's a good thing to know. And then I have added 2 cases. Probably what I see is that's not needed here, but yeah, I just coded it up. If CT1 is less than CT2, then what do you do? Your temp equals to num of 1, because I need to traverse the number, right? I need to traverse the number. And diff equals to how many extra ones do I have? So my answer starts from num1, because as I told you, right, I can make the number of set bits will be the places where I need to put ones will be where num1 already has ones. So that is why I have initialized my answer with num1, right? So that I can take some ors and all, and I'll be good to go. I have taken a variable 2 so that I can left shift and calculate, while temp is greater than 0 and diff is greater than 1. So what I have checked, if temp mod 2 equals 0, that means if at current position in nums1 I have a 0, then that means you place a 1 there, because you still have ones remaining, and you do diff minus minus, right? And then you divide temp by 2 and multiply 2 by 2, just to assign the exact weightage to that particular position. Now again, a tricky case here, while diff is greater than 0, so there can be a possibility that you have your nums1 becomes 0. You have traversed the whole number, but still you have ones remaining, as I showed you in one of the examples in the diagram. So what do you do? That's why on line number 43 I have ran an extra loop while diff is greater than 0. You do that you keep on adding the new weightages and decrement the diff and do the needful, and finally you return the answer, right? On line number 51, I have done it to basically tackle the third case. That is where CT1 is greater than CT2. So you calculate the number of extra ones that you have. Actually, that is not required here. That is not required. I probably was doing something else. So line number 51 is not required. We are interested in the number of set bits that the second number have in this case, right? So while CT2 is greater than 0, what do? You calculate the leftmost set bit weightage. So get leftmost set bit number. So I call this function on line number 11. If n equals to 0, return 0. And then you can see MSB equals to 0, n equals to n by 2, while n is not equal to 0. I keep on doing these things, right? And finally I return the number of the weightage, right? Easy stuff. So answer plus equals to x, right? I do that. My answer is initially 0, and I know what is the leftmost bit. I need to place a 1 here. That means I add that power of 2 to my answer. Now I decrement count to minus minus, and then again num1 and equals to x minus 1. Because why I am doing this? because I need to remove that number. Now I need to remove that number, and to remove that, I need to remove that particular bit, right? And that bit will be removed. What I mean to say, let me just show. So suppose there is a number 1100. If I need to remove it, so what I can do, right? What I can do, I can place a 0 here and 1111 here, right? So if my number here is a power of 2, what is the power of 2? 100 and number of zeros. If you do -1, what you get? You get 0 here and n minus 1 number of ones, right? So that is why what I have done, I know what is the leftmost power, so that is a power of 2. I do that -1. So if there is 12, this will become, I take end, and then, so just see what it becomes. And finally, I know that my nums1 will be equals to 1, 0 and 0. So this is a trick to remove the leftmost bit, right? So yeah, that's what I've done in my solution. Finally, I return my answer, right? So yeah, I hope you learned something new from this video. Lots of problem related to bit manipulation. So in case you have any queries, do mention that into the comments. I'll try to revert on each one of them. If you find this channel useful, then do subscribe to the channel. It helps me keep motivated. Also, if you like this video, do support it by giving a thumbs up. Yeah, see you in the next video. Bye bye.